Thanks to Lori for sharing the stage here this morning, and thanks to everybody for giving me a chance to come and talk a little bit about a few things from the Astrophysics division side that I think that the folks here will be interested in. My name is Doug Hudgins. I am the program scientist for our Exoplanet Exploration program. That is part of the Astrophysics division, and understanding that NASA headquarters is probably at best a black box for most people, and the best people tend to do is to understand the division of the Science Mission Directorate that you're most closely associated with. I thought it was probably worthwhile since many people here are going to be most familiar with the Planetary Science Division, just to sort of introduce you to the Exoplanet Exploration Program. It's one of 3 science-themed programs that we have within the Astrophysics Division. We have a program scientist and a program executive that oversee it with the help and support of the Exoplanet Exploration Program Office, which is located at JPL. And basically the ExOP office is the people that implement all the various aspects of the program. The Exoplanet Exploration Program serves the NASA community by acting as a focal point for exoplanet science and technology, managing a portfolio of research and technology development activities. We facilitate access to scientific data, and also we support integrating the results of previous and current missions into a cohesive strategy for future discoveries. I also want to introduce the Exoplanet Program Analysis Group to the folks here. As you know, the ExOPAG participated with the OPAG and VEXAG in organizing this meeting, and I'm really pleased that that's the case. I suspect that the ExOPAG, most everybody probably knows that it exists. I'm not sure many people have experience with the ExOPAG, but we would like to build more interaction between the planetary science community and the ExOPAG, because in fact the Exoplanet program, studying exoplanets, well, up to this point in history, we have done a lot with the detection of exoplanets. As you well know, we are at the doorstep of moving into the time when we are going to start characterizing exoplanets. And of course, at that point, although the Exoplanet program, we're using the tools of astrophysics, basically, big iron space telescopes, we are doing planetary science, pure and simple. So in fact, everything from the science that we are doing is planetary science. The design of our future missions needs to have a fundamental understanding of the planetary science, the measurements that we need to make. So it's really important to have strong involvement in from the community, the planetary science community, in the Exoplanet program. So basically, the ExOPAG is a community-based interdisciplinary forum for soliciting and coordinating community input and analysis in support of our exoplanet exploration activities, and of their implications for architecture planning and activity prioritization for future exploration. The ExOPAG is a forum that enables direct, regular communication between NASA and the community through public meetings that give the community opportunities to provide its scientific and programmatic input. Generally, we have 2 meetings a year. One is always held in conjunction with the winter meeting of the AAS. The other meeting is generally in the summertime at some point, and we try and piggyback on a meeting that addresses maybe a community that, area aspects of the community that are not well represented at the AAS meeting. So for example, we've done ExOPAG meetings in conjunction with AbSciCon before. We've even done one in conjunction with DPS before. So oftentimes we try and schedule that summer meeting in conjunction with either an astrobiology or a planetary science meeting, again, because we understand that this community may not be as well represented at the AAS meeting, and it's important that we have involvement and participation from the planetary science community. The ExOPAG consists of all members of the community who participate in the open meeting. So to be a member of the ExOPAG, you have simply to walk in and sit down in a meeting. The ExOPAG reports its findings and analyses to the Astrophysics Division Director and the Astrophysics Advisory Committee, and the ExOPAG Chair is a member of the Astrophysics Advisory Committee. The ExOPAG Chair is supported by an executive committee which helps to capture and organize the community input, keep the community informed of ongoing activities and opportunities, oversee ExOPAG science analysis groups and science interest groups, and prepare ExOPAG findings and inputs for presentation to Paul Ertz. EC members are appointed annually to serve a 3-year term. The ExOPAG EC is constructed to reflect the broad range of scientific disciplines and interests represented in exoplanet exploration. So here again, we solicit nominations for membership in the ExOPAG EC annually. Unfortunately, we just closed our call this year back in the middle of January, but there will be a call coming out next fall again. And I encourage people, if you're interested in being part of the steering committee for the ExOPAG, we definitely like to have representation from the planetary science and the astrobiology community on the panel. All right, so I want to talk a little bit about planetary science opportunities that are going to be offered by future NASA astrophysics missions. Before I go on into that, though, I want to mention, of course, you should be aware that that NASA's astrophysics portfolio includes missions and ground-based telescopes that accept proposals to do planetary science. So the Keck Observatory, of course, the IRTF, all of NASA's observatories, particularly the Hubble Space Telescope, the Chandra X-ray Observatory, and the TESS mission, all have significant programs to do planetary science. And one of the things that I want to address specifically is I know that there is the scuttlebutt in the planetary science community is often that, well, you know, you can't get, you know, that planetary science doesn't really get a fair shake in the review of proposals for these astrophysics missions. And I assure you, we've looked at that, we take that very seriously, and we've looked at it, and in fact, in all of these missions, the success rate of planetary science proposals is indistinguishable from the success rate of astrophysics proposals. If planetary science is underrepresented in the overall science program of the mission or the observatory, it's because we aren't getting many planetary science proposals. So one of the concerns we have is that there's great planetary science that people are that people are feeling discouraged and not proposing to our missions. And I want to encourage you to please go ahead, write your proposal, put it in. These are obviously Hubble time is a very much sought after commodity. But the fact is that you are not at a disadvantage proposing planetary science. And we want to do the best science with our observatories. And of course, that includes planetary science. So looking forward, of course, the next great observatory is going to be the James Webb Space Telescope, which is a 6.5 meter telescope, which is going to operate in the near and mid infrared from about 0.6 to about 28.5 microns. You know, so this is sort of like a bewildering plot that you can stare at, and it just shows all the different observing modes that are going to be available with the Webb telescope. There are 4 instruments: NIRSPEC, a near-infrared spectrometer; MIRI is the mid-infrared instrument; NIRCam, a near-infrared camera; NIRIS is basically the fine guidance sensors from the observatory. And basically the takeaway message here is there's imaging capability in multiple bands. There is spectroscopic capability, both low and mid resolution, up into the few thousand sort of range, that is going to be available all across this wavelength range. So there's lots and lots of science that is going to be available to do. One of the top level goals of JWST is determining the physical and chemical properties of solar systems, and that includes our own solar system, and where the building blocks of life may be present. Tracking rates for planetary science have been built into the observatory. It's a requirement that the observatory be able to track at 30 milliarc seconds per second, which allows it to observe Mars. And the goal is actually to have faster tracking rates, up to 60 milliarc seconds per second. And that was actually offered as part of the Cycle 1 call for guest observer programs. And they're going to be, as soon as we get launched and during commissioning, they're going to test the tracking rate as to what they will actually be able to achieve. But because of the fast tracking rate, this opens up a lot of opportunities for solar system observations. Of course, you might say, well, why do we need space telescopes when we have directed missions that go to these objects? Well, in general, as you know, it's a great luxury to have a mission that actually goes to the planet and hangs out there, such as Cassini, and past missions to Jupiter, and that's a great luxury. But it's also a limited period of time. You have a few years while that goes on. But it actually, Cassini had a great run, but nothing lasts forever. Well, this is an opportunity that you can observe all the planets. You have your gap with Uranus and Neptune, the outer planets. You'll be able to observe them with Webb. I actually had a great image that didn't actually make it into the final cut here that shows the pixel array overlaid on Titan, and you get, like, when you point Webb at Titan, you're going to get like 150 pixels across the disk. So it's going to be much better resolution than we've had available, and of course that will not just be, each of those pixels will not just be a measurement, photometric measurement. It'll also be spectroscopic. So a lot of science is going to be available, and filling in gaps in areas that you don't have an observatory active. And also you get an opportunity in places where you have a mission, around a planet. You can also provide supporting observations. Sometimes the global observations can pair with the more focused observations of the mission in orbit around the planet as well. So there's a variety of reasons why having the availability of a space telescope like this is a value to planetary science. So just a quick list of some examples of the sort of science that you'll be able to do with JWST in the solar system. You're going to be able to do instantaneous measurements of the whole observable disk of Mars at very high spatial resolutions, and that's going to allow for investigations of transient events near the day-night terminator, both diurnal east-west sort of effects and seasonal north-south phenomena. And you'll be able to see the rapid vaporization of polar ices and other volatiles from the surface. So a much more, a great way to study the transitions that are occurring across the surface during either day-night changes or seasonal changes. The 4 MIRI medium resolution IFUs will produce spectral maps for all gas giant and ice giant planets in the outer solar system, as well as their moons. I just mentioned the image of Titan as well. High resolution spectroscopy towards active plumes in the solar system will reveal new insights prior to a directed mission on composition and enable searches for surface variations before and after activity occurred with imaging and spectra. And finally, JWST will be able to characterize every known Kuiper Belt object to date. So lots of good science, and of course you all can think of 7 different things that I didn't even put up here. So again, lots of good things to do. There will be solar system science done right out of the gate for JWST. 2 interdisciplinary scientists on the JWST team have solar system interests. That's Heidi Hanel and Jonathan Lunine. Heidi has dedicated 100% of her time to solar system community, and she's going to be observing things like asteroids, NEOs, comets, Mars, Jupiter, Saturn, Uranus, Neptune, you name it. And the proprietary period is going to be waived on that data, so it is going to be released as soon as it's pipeline processed. You can find details. There's a link here for finding details on the GTO program. There's also an early release science program that titled Observations of the Jovian System as a demonstration of JWST's capabilities for solar system science. Imke de Pater of the University of California, Berkeley is the PI on that, and basically it's going to focus on characterizing Jupiter's cloud layers, winds, composition, auroral activities, you name it. Again, a lot of science of the Jupiter system. So good science is going to be done, and of course you can put yourself in the future guest observer cycles for the Webb Space Telescope. You can put yourself in this picture. After Webb comes the Wide Field Infrared Space Telescope, or WFIRST. It's going to be a 2.4 meter space telescope operating at near infrared and visible wavelengths. It's very similar to the Hubble Space Telescope with the exception that it has a 100 times larger field of view. So it's going to be perfectly equipped for doing survey sort of science. It has a 6-year mission and it's planned for launch in 2025. It has 2 instruments, the Wide Field instrument, which is a 288 megapixel camera operating between 0.7 and 2 microns, and then the coronagraph instrument, which is capable of suppressing starlight and directly imaging exoplanets. So this is not the mission that will get us down to studying exo-Earths. It is a mission that will be able to study, say, planets as small as maybe Uranus and Neptune on a few AU orbits around their star. So in fact, there's good, whereas the news media may not get excited about looking for life on on Earth 2.0, there's going to be lots of planetary science to be done here with the coronagraph instrument. The WFIRST, the baseline is going to be doing a survey of gravitational microlensing. You may understand that gravitational microlensing is an exoplanet survey. It's for exoplanet detection, and it is a way to survey the outer parts of solar systems, say, so from 1 AU out. You realize that the missions that we've done so far, relying heavily on transit detection or much of the work that's been done from the ground with radial velocities, is sensitive to planets that are close into their star, generally within 1 AU. So the microlensing survey will provide the complement that we've been lacking to the transit surveys that we have of exoplanets. And we'll really understand what's going on beyond 1 AU in other solar systems, and how does our solar system, again, coming back to how does our solar system compare to other solar systems? Are we similar or are we different? That's what will come out of that sort of study. Example, planetary science investigations. You will be able to study Earth Trojans, which are important because they're close to us, and they're difficult to detect because of their small solar elongation angles as seen from Earth. And the inability of space telescopes generally to point, anywhere that even approximates toward the sun. So fortunately, Earth Trojans at L4 or L5 would be at solar elongations of about 59 degrees, and that is within the field of regard that will be allowed for WFIRST. So it'll actually be able to do that sort of observation. Another thing is studying irregular satellites. The WFIRST Wide Field Instrument will enable deep, efficient searches for new irregular satellites of the giant planets. And there's a number of observations of Jupiter that have been proposed. And you can see here different pointings at Jupiter, Saturn, Uranus, Neptune, and different times and things like that. And that will actually enable the detection. And the black spot there, which you really doesn't show up very well, is the full WFIRST field of view. Inside that black box is actually the arrangement of detectors for WFIRST. That's the full field of view of WFIRST. So you can see it's going to be able to do to really good observations of the planet itself, and as well as its vicinity, surveying its vicinity for irregular satellites. Also, it'll be able to do an inner Oort cloud search. with different pointings. Again, wide field of view allows you to pick up these, and great sensitivity allows you to pick up very faint objects that are moving in the outer solar system. And just looking further down the road, these are the 4 large mission concept studies that NASA conducted in the run-up to our Astro 2020 decadal survey. They've been submitted and they are under consideration. The 2 on the left, the Habitable Exoplanet Observatory, HABEX, or LUVOIR, the very fancy sounding name for Large Ultraviolet Optical Infrared Space Telescope. LYNX is an X-ray observatory. Origins is an infrared and far infrared space observatory. All of these things, all of these would have obviously tremendous potential in the future for solar system observations. And in fact, the science case for solar system science with each of these missions was considered and is in the reports for the observatory for each one of these things. And if you're interested in looking into those, you can find the reports at the science.nasa.gov website and look into what their capabilities are. Okay, so I want to talk a little bit about the changes that are coming to RNA programs in particular, because this will, of course, affect the people in the room. Now, you're gonna look at this and you're gonna say, wait, didn't Lori already show the slide? I want to point out to you this is not the same slide. Lori's slide was blue. So for those of you, I would like you to take comfort in the fact that at least we have our story straight, right? Which isn't always the case for headquarters. So anyway, talking about the Exoplanet Research Program, of course, Lori mentioned that we have moved to a rather than just a confederation of 2 city-states, we've now moved to a real joint management scheme for the program that involves now all 4 divisions of SMD. So that happened this year. It's working well, and we will continue to go that way. In 2020, also in the Astrophysics division, we've made the decision that we wanted to consolidate our exoplanet science research into a single program, the Exoplanet Research Program. We made that decision because we really want to, that includes science that was previously solicited as part of our Astrophysics Data Analysis Program or the Astrophysics Theory Program. We made this decision because we want to select the best exoplanet science, and we want to evaluate what the best exoplanet science is in the context of the whole, all the exoplanet sciences proposed. As we're doing it right now, we're in the Astrophysics Data Analysis Program, for example, we're selecting the best exoplanet science amongst all in the context of all astrophysics. So it's a bit of a change. We want to bring together the exoplanet science into one area and choose whether it's data analysis, theory, ground-based observing, you name it. We want to choose the best exoplanet science blind to that. Obviously, I know that everybody, you heard Lori mention this with Hab Worlds. I'm mentioning it with ADAP and Astrophysics Theory, and everybody is now hyperventilating because they saw the low selection rates that we had for XRP last year. And I want to assure you that, in fact, we will be moving money behind the scenes to support the added scope that we're putting into XRP. So this is not something that we expect to drive the selection rate down. So I want to reassure you about that. And so I think Lori talked about the rest of this pretty well. The other thing that's coming is the dual anonymous peer review. So SMD is strongly committed to ensuring the review of proposals is performed in an equitable and fair manner that reduces the impacts of any unconscious bias. And to this end, you may be familiar with the paper that was published. The Hubble Space Telescope Guest Observer Program basically conducted its own study, its own program, and developed a dual anonymous peer review process to use in their program. They've done it a couple of times now. They actually published a paper discussing the process in great detail, and it has been successful for them. As a result, we are in SMD, we are going to be doing a pilot program to begin integrating the dual anonymous peer review process into our ROSES solicitations. Under the dual anonymous, as the name would suggest, dual anonymous peer review, not only are proposers unaware of the identity of the members of the review panel, but the reviewers don't have explicit knowledge of the identities of the proposing team during the scientific evaluation of their proposal. Why is this an important thing? Well, this is a plot from the Hubble Space Telescope looking at the results for various cycles broken down by gender as concluded by the names of the PIs. So you can judge, in most cases, the gender of the PI by their name, and that's what they've done here. We didn't ask for demographic information in this case. And what you see is there is consistently from cycle 11 through cycle 27 down here, there is consistently a small difference between the selection rate for PIs with male-sounding names and PIs with female-sounding names. Usually it's on the order of 2 to 5%. It is a small effect, but of course, if you look at it across, this is a period of 16 years. A small effect year upon year upon year upon year adds up to a significant impact on the community, the diversity of the community, because in some sense, proposal success is a proxy for whether you stay in the field or not. If you're not successful in the field, you move on to another job or things like this. So going on year after year after year, the small selection effect every year is eroding the diversity in the community. And then they show, here's the results for 2 years after the dual anonymous. It's very tempting at this point to say, oh, well, 1 year it went one way, 1 year it went the other way. Well, it's going to go back and forth. We'll see over time how successfully that plays out. But it is important to do this because the effect is real. I also don't want to give the idea that the only thing that we're concerned about is gender diversity. There's obviously many different aspects of diversity of the community. We're concerned about all of them. This tends to be the easy one to measure because you can simply look at names and say male-sounding names and female-sounding names and get some data on it without asking for demographic information, because they tend to get, the lawyers get really touchy about what you can do with demographic information that you collect. But here's another way to look at it. This is success rate for ROSES programs in this pilot that we're doing for the programs that we're doing, and you can see starting all the way from PIs who are government contractors, PIs at NASA centers, PIs at federal government institutions, Research 1 institutions, nonprofits, Research 2, non-R1, R2, and then minority serving institutions. That's real. And it's a big effect. This is another aspect of diversity, just the range of institutions that people are at. So it isn't just a gender thing that we're concerned about. We know this effect exists, and we know that it is, and we want to try and find a way to get around it. So we are going to the dual anonymous peer review. Basically, I've already said, obviously the reviewers don't know who the proposing team is. The primary intent of the DAPR, as we call it, DAPR, is to eliminate the team as a topic during the scientific evaluation of the proposal, not to make it absolutely impossible to guess who the team might be. So again, what we're going to do is people are going to submit proposals in an anonymous format. That doesn't mean that everybody isn't going to, that you might not, if you tried really hard, be able to figure out who it probably is. That's not what you're supposed to be doing, by the way. But it is to take that out of your view while you're evaluating the proposal, and it creates a shift in the tenor of the discussions away from individuals toward discussion of the scientific merit of the proposal, which is where we want it to be. So we're taking several steps to ensure a smooth transition. We're creating written guidance on how to write an anonymized proposal. This is actually, I say this is the Astrophysics division, but this is actually true much across all the divisions. We will be hosting a virtual town hall in 2020 to discuss the dual anonymous peer review with the community. I can tell you from the Astrophysics division that the last week in February, the guest observer, guest investigator programs in Astrophysics, we will be having a town hall for proposers for all of those programs. About a week or two after that, so early March, look for the announcement coming out from NRS. In early March, there will be an SMD town hall for all SMD proposers. And then I can speak for my program, the Astrophysics Data Analysis program will be doing the Dual Anonymous, which is the program that I run in Astrophysics. We are going to be doing a virtual town hall for ADAP proposers the first week in April, right after the NOIs come in. I wanted to do that because that will be, the proposers for ADAP will then have had their oh shit moment. Oh my God, this is really happening. How do I do this? And so right after the NOIs come in, then we'll have that peer review. And I expect that you will find that across all the divisions, we'll do this sort of town hall to educate everybody on how this is going to work and how you're going to write your proposal in this new format. Basically, the feedback that Hubble has gotten on this it has been uniformly positive. Basically, you can see some quotes here that basically it shifted the tenor of discussions away from the people and back onto the science where it belongs. It actually made the discussions more congenial because they're less personal now. You're not talking about individuals that you like or don't like or whatever, and you don't have the same personal contact with it. So it's definitely a step in the right direction. I expect that we are going to have to learn together. I, as a program officer, am going to be doing this for my first time, and we have to adapt the NSPIRE system to work in a dual anonymous format, and we've worked very hard behind the scenes to set up a process that I think is going to work well. We'll have bumps along the way, and then of course on your side, learning to write your proposals in a new way will also take some practice and education. But together, this is the right thing to do. It's going to get us to a more objective peer review, and that's the goal that's the right goal to be working for.